Right, welcome back, class. I hope you have tried out the XOR gate models from the previous lectures. So, what we had done was use the assign statement and simulate the combinational logic resulting in an XOR gate. In this session, we will start with similar modeling for the full adder and go on to use a next procedural statement called the always block. We will use the always block to simulate a full adder. So let's begin. Let me just I'll call it FA.V. So full adder. So the design principles will be very similar to the XOR gate. I will pretty much use the same assign statements to demonstrate that this works correctly for the full adder also. So this is the equation that we want to simulate, right, for the sum and the carry. So the outputs of the full adder first, say the sum and say carry out. Then inputs are A, B, and carry in. Right. So this is the input. Input is A, B, carry in, and output will be sum carry out. So that's it. And you now know that both input and outputs are of type wires, and because they are type wires, you can directly use the assign statement to drive the output wire. And all I have to do is to just write this full equation now. So let me just do that. So A bar and B bar and carry in, or I just use the same this is correct. The next one is x y z bar. So x bar y z bar, x bar y. Yeah, so it's A bar and B and C bar. Then it will be A, B bar and C bar, and finally A, B and C in. So that is the correct sum statement. For the assign, it will be carry in AB plus BC plus CA sort of an equation. So let me just put that A, B, or AB and carry in, or C and so carry in and A. Yeah, so that's the carry in statement. So that is the full adder. That's it. So let me see if this compiles correctly. So I've just created fa.v. So I verilog fa.v so that there's no problem with that. We'll do the test bench also in the very similar manner. Right, so let me just create a new test bench now. So say fa underscore tb.v, yeah, test bench for the full adder. So yeah, so you know the test bench is a standalone program that is used to pass stimulus and to monitor the output to and from the design and the test. So it's fairly straightforward to write the local nets of the test bench. What I've just done is copy the inputs and output lines into the test bench. So thereby the same names are preserved. All we have to do is to change the input or the input ports have to be fed by a reg, by the reg nets. So just change the input to the outputs that are coming out of the design under test have to be drawn out through wires, and that's what we have done here. The next is to instantiate tut, and this also is actually straightforward disk copy module declaration. So this is the module that we want to instantiate, and I just call it fa1 just to give it a name. And the order of the names of the nets created in the test bench is the same, and the order in which they have to be sort of called are also the same. So this statement is now accurate. Then we will feed stimulus, and also of course put a monitor statement inside. So I will do that inside the initial block. The monitor. So let me just write the stimulus for A, B, and carry in first. Right. I'll give a delay of 5 and then write just A of 0. And we know that there are 3 inputs, so there will be a 7 possible combinations of these inputs. So, and this is of course straightforward. You can change the order of inputs in any manner, but this is just, I'm just sort of writing out the truth table example, and we'll give some more delay before we say finish the simulation. That will be monitored now. The first field we usually print out is the time, and we print out all the 5 variables. So starting from the inputs, this is the inputs, and the output will be sum. The same way let me just put the carry out first, because this was carry out, and then sum. That's the monitor statement. So in terms of test bench, I believe that is all. You can write the BCD dump lines. Go ahead and write it for this demo. So let me see what I've done. So that is there is an FA underscore test bench here. So by Verilog FA underscore p. Yeah, there are no errors except that, of course, we have not. So the Verilog doesn't know where the FA module is defined, so now both of them are compiled together. So I should have a brand new dot out. So let me just run that. There is a okay. So first of all, let's look at this. There is an error here, so we'll try to debug this. So at time t equals 0, no inputs have been given. So the inputs are x, which is don't care conditions, and the output will also be sort of indeterminate. Actually, sum is equal to x. So that's. But if you look at after when we initiate or when we initialize inputs after 5 time units, that is a equals 0, b equals 0, c equals 0, the sum output is corrected. The carry output is high impedance output. So this is one of the features of Verilog. There are 4 values for a bit. Apart from 0 and 1, there are 2 other values, actually x and z. Z means a high impedance output, and x is basically metastable output, which is the simulation is not able to figure out what the output is. So there is some sort of a problem in the code. Let's see. So So in the assign statement, you might have already noticed while in the video, but I did not notice this, so I left the carry in as the LHS actually, so it should have been carry out. So let's see if syntactically that was not wrong, so it didn't pop up an error at that time. So now I've just recompiled it. I've changed this to carry out, and then just recompiled it. Let me see if this works now. Okay, yeah. So now this seems correct. Just verify this behavior is right. So that is one way of writing. So uh, let's do the always block now, right? So if you've looked at the PPTs from the XOR gate videos, um, in the slides for comparison between REG and wire outputs, you can see more information about what a reg is, right? And that is now important when we are writing the always block. So let me just start off, right? So let's see, I will rename this as FA always because I'm using the always block, right? So let's see the name of this. Right, before we replace the assign statements with the always block, we'll just look at what the assign statement is doing once again. Right, so the assign statement simulation, Verilog simulation, has created a combinational circuit that drives the signal sum using the logic on the RHS of this equation, right? This is the right hand side of the equation selected. So what actually happens in simulation is when any of these signals on the right hand side of this equation change, the assign statement is executed and the sum is re-evaluated and it is re-driven in some sense, right? So a new value for the sum is re-evaluated and assigned to this. So the key fact here is that the signals A, B, and carry in, whenever these change, the assign statement is re-executed. And this is a common trend, this is a common concept in most simulations, and the idea behind this is called the event-driven simulation. Based on a certain event or based on a bunch of events, a simulation event or a simulation takes place, right? So, and in this case, this event is driven by the signals in this particular assign statement. These events are basically the change in signals. In the signals are A, B, and carry in. When one of these three signals change, so the desired event is said to have occurred, and the assign statement will be executed when this event occurs, right? So the same idea applies to the always block also. So we will now basically replace the assign statements with an always block. There are a few more rules here which we will meet as we go through. So ideally what should happen is just so much. The behavior of the sum and carry out does not change. So we are expressing the behaviors in exactly the same manner. However, we are now removing the assign statements and putting it inside an always block, and very clearly or explicitly mentioning the list of events that can trigger this always block. So what we should now include as parameter inside the always block is a sensitivity list. What a sensitivity list is, basically the list of all signals that whenever this signal changes, right, the following two statements or the statements inside the always block have to execute. So yeah, so let me just repeat that again. What the always block does is this block of code in between the begin and the end statements will get executed when one of these signals change, and we are interested in generating the sum and the carry when one of these inputs change, right? And these inputs are a, b, and carry a. So that is it. In translation from the assign statements to the always block, that is all that has to be done, right? We just mentioned the sensitivity list here. There is one extra concept which will come up while we are compiling the code. So let me just compile the code to see if there is an error here. I will not fa, right? We're compiling the always. So there is an error in line number 11. Sum is not a valid L value for in this module. Sum is basically declared here as a wire, and if you see that the second error is also the same, it's for carry out. So both sum and carry out are in lines 11 and 12, where they have been used inside the always block as the LHS, right? And you also know that output and input create nets of type wires. So this is where the always block differs from the combinational logic assign statement. Is we have to explicitly declare these output variables as reg inside the always block whenever we use a signal in the LHS, that is these two, sum and carry out, they have to be declared as reg nets. This is one way of doing it, output reg and then this, or I could do this also, reg sum and carry out. This is also fine. So let's do this, right? So the rule is inside the always block, any signal that comes on the left hand side has to be declared as reg, right? So let's see if this works. So that's it. So if you notice from the previous XOR gate slides, this rule has been mentioned in the reg versus wire slides. You can go through those slides, and there's some very important information there. So now that we have executed this, I will also execute the test bench with this. Let me see, the test bench is here, fa always, yeah. So this is fa underscore a, and the test bench is here. We are instantiating fa here, so I want to just instantiate fa underscore a correctly. So that's done. So as you can see, there is no difference in the output. Yeah, so this is the first code that with the always block, right? So just to quickly recap, the always block requires a sensitivity list. You can alternatively just write at star, means at any when any of the signals change, then this always block will get executed. Here we've very specifically written the three signals that we're interested in. When they change, the output should be re-evaluated, right? And these are the statements, and they're very similar to the assign statements. Basically, we've written the logic on the right hand side and the output signal that will be re-evaluated on the left hand side. So yeah, that's the use of the logic block. Next, what we will do is to use this working full adder, right? And cascade 4 of them and make a 4-bit full adder. In fact, you already have enough information and enough Verilog to do it. However, we will use arrays in the inputs in the 4-bit full adder, so that will be the new concept next.